operators, how do you define some braiding operation for two of these particles? And also, it's not clear what phase equivalence relations you should use. For example, like to get from a fracton system of size L to a size L+1, the ground state degeneracy changes. How do you do this smoothly? Well, one way is this definition of foliated phase equivalence by Shen, which is basically you can take fracton model, you can add another torque code layer on top of it, and then by local unitary transformations, you can now use this to sort of grow your fracton phase by one. But it's not clear what the most natural phase equivalence relation should be if you want to classify fracton phases. And actually, if you don't have like some translation symmetry or something, there's actually uncountably infinite fracton phases. So then, sort of, you really require some additional phase equivalence relation other than just like standard local unitary transformation. Okay, so that's a sort of a big goal, but I'm going to approach this by saying, okay, let's forget about this for now. Let's focus on a smaller question. Can we possibly classify fracton models if we restrict to those models with a particular underlying structure? So this is some subset of fracton models, and what I mean by this underlying structure is, can we classify all fracton models that are dual to models with a particular set of subsystem symmetry? And I'll tell you what that means. Brief outline. So first I'm going to go through this duality relation between subsystem SPTs in 3+1 dimension and fracton phases. And then I'll see what general statements I can make about fracton duals of these subsystem SPTs. And then I'll go on to show you how you can construct these SSPT phases. They correspond to all sorts of twisted fracton models. And in particular, I'm going to define what I mean by weak or strong subsystem SPTs. And sort of everything will be discussed both on the SSPT and the fracton dual side. And most of these results are in this recent paper with myself, Wilbur, and Juven. So let me go over this duality transformation real quick. Probably don't need to do this, but let me just review how this gauging duality works in 2D. If you start off with a 2D transverse Ising model, there's just, you have your Ising coupling, you have your transverse field, and it has a global Z2 symmetry that involves acting with X on every site. When you gauge, all you do is you introduce this gauge field on your links. You modify your terminal term like this, and then now you also have a gauge invariance, which is generated by some operator that looks like this. You can flip any spin, but now you can also flip all of the gauge spins on the links next to it. And now what you can do is you can gauge fix to the physical. You can use this to sort of gauge fix all the physical spins to be +1. Then you end up with a Hamiltonian that looks like this. And if you go to the paramagnetic limit of the original model, h goes to infinity, you end up with just these two perturbatively, and that's the toric code. So in this sense, I say the Ising paramagnet gauges to the toric code. And so this is what I just went over. But more generally, if you start off with some non-trivial paramagnet, for example, this Levengood paramagnet, which is a non-trivial Z2 SPT, you gauge this, instead of getting toric code, you get double semyon, which is another type of topological order. So toric code has two bosons and a fermion. Double semyon has a boson and two semyons. And more generally, if you start with some two-dimensional global SPT, you gauge it, you get some topological order. And this is exactly the same relation between subsystem SPTs and fractons. Except it's a slightly different gauging procedure. So you start off with, let's say, this three-dimensional plaquette Ising model. You're on a cubic lattice in 3D. You have four-body interaction Z, 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 Z on each plaquette like this of three orientations. And this model has what I call a subsystem Z2 symmetry, which is you just product over all sites in a plane of X. It always overlaps with exactly 2, 4, or 0. Z's, so it commutes. So to gauge this subsystem symmetry, this was this paper by Vijay Hafu. you introduce this spin at the center of plaquettes instead. And then you can go through all the same steps as before, and you can also go to the dual lattice, and what you end up with is this X-cube model. So this plaquette Ising paramagnet in the paramagnetic phase gauges to the X-cube model. The X-cube model is this exactly solvable model of Fracton topological order. You have degrees of freedom on your links. And you have two terms. One is this cube term where you have x's on every bond of this link. And the other one is these z terms where you have z's on four bonds that come out of a vertex, and it can be of either one of three orientations. So these terms operate with each other, and you can solve you can solve exactly. And you see that there's two types of quasiparticle excitations. One is if you act with, say, all z's on all of these bonds on a membrane like this, this operator commutes with all the x's except for those four at the corners, and so this creates four excitations at its four corners, and a single one can't move by itself. You can also have what I call a line-on, which is a one-dimensionally mobile particle. If you add x's along a line, this anti-commutes with a pair of z's at its two endpoints, and so this can move along the line, but if you try to turn this, then it'll end up leaving some excitation behind at the turning point. So this is what I call a line-on. You can also have plane-ons that move along planes, and these can be constructed sort of as a pair of fractons or a pair of line-ons. And in exactly the same way as with global symmetries that I showed before, if you start off with a non-trivial subsystem SPT, you go through this gauge duality, you end up with some twisted X-cube model. And you can also, and sort of this class of Fracton models is what I want to focus on. It's a potentially tractable set of Fracton models to deal with. So by understanding sort of the classification or what types of possible subsystem SPT phases you can create on this side, we can also sort of understand what's going on this side, in the Fracton side, and sort of gain insight to the structure of Fracton phases. I just want to mention that this is all in 3 dimensions. In 2D, subsystem SPTs also exist, but Fracton topological order doesn't. And SSPTs are also quite interesting in 2D, but not, yeah.
So can I just ask the obvious question of why don't you get Fracton order in that case by gauging the?
Well, you're not going to have topologically protected graphs to degeneracy. And 2D, you just have regular topological order.
But what about the usual argument of once you gauge, things should no longer be, like if they were not equivalent with symmetries?
It's like topological order in 1D, right? If you have no symmetries, you can't have topological order in 1D. Well, the Z2 fermionic symmetries. Yeah, it's sort of one-dimensional higher, lower than usual topological orders.
Can I roughly think of it as saying that if you gauge a 2+1D subsystem SPT,
you end up with
a confined phase?
Yeah. Well, okay. Yeah. You don't get topological.
You don't get a deconfined phase.
Yeah. Okay. So what do we know about Fracton models that are dual to SSPTs? So let me first just start off with some definitions. I'm always going to work on a cubic lattice, and there are symmetries that can act on, say, only the xy plane, or xy and yz, or all 3 directions. And these 3 cases are what I call one-foliated, two-foliated, three-foliated symmetries. And your symmetry operation is going to be just a product of some on-site representation of your on-site symmetry group. So, and in this talk, unless otherwise stated, I'm always going to be focusing on this 3-foliated case with G equals Z2, the simplest case. But all the generalization can be generalized to sort of all 3 of these, and also finite abelian symmetry groups.
Is it important that this cubic lattice?
Not really, but sort of, I've only worked on cubic. You can define like fancier lattices, but you need some way to define the subsystem symmetries on that lattice.
Okay, so changing lattice type, is it just a technical triviality, or does it lead to new phases?
It could lead to new phases.
Okay.
Because the structure of the subsystem symmetries.
Yeah, that's
okay, so what we know, well, first of all, excitations that carry charge under subsystem symmetries must be fractons. So if you have some quasiparticle excitation here that carries charge under this planar symmetry, and this planar symmetry, it's just by conservation of charge, it can't move without like creating some charge-anti-charge pairs and other excitations. It basically is stuck here. Similarly, if you have two of them in the dipole, this does not carry any charge under any of the orthogonal subsystem symmetries, only the this is xy planar symmetries. So this is free to move in the xy plane. And so from this, we know that whatever fractal model we end up with, the charge excitation must be fractons, dipoles must form planons, they must all have trivial mutual statistics with each other. And okay, so now what about the possible gauge flux excitations? Well, you can sort of think of gauge fluxes as coming from sort of symmetry defects. So if you look at a single planar symmetry on your SSPT side and you sort of truncate it to some region, this corresponds to sort of moving a symmetry defect along the boundary of this region. And so what you can conclude from this is that, well, gauge fluxes must exist, planons must exist. So there must be some combination of gauge fluxes that can move along a two-dimensional plane that will enact this transformation. Naively, you might also think, okay, well, I could also act with a symmetry on a truncated cube like this, and this looks like it's moving symmetry defects only along the edges. And this would lead to the fact that gauge flux linons exist. But that's actually not true generally, and there's a subtle reason why this argument doesn't work. Right. So all we know is that the gauge flux excitation could either be linons or fractons. It really depends on what model you write down. But sort of pairs of them have to be planons by that argument. And for simplicity, I'm just going to focus on models where you do have linons, because they're more familiar. Okay. Any questions so far? Okay. So let me now show you how to construct non-trivial weak SSPTs. And the way I'm doing this is just by sort of bootstrapping results from lower dimensions. So suppose you have a 2D regular SPT, global SPT, on the square lattice. For Z2, this would be the Levengood phase, and it's written down as some wave function with sum over all possible configurations of Z's and some amplitude in front of them. And you can always construct any phase in this form. So, you can even construct like some exactly solvable ones where F is just a pure phase, and you can write down a commuting Hamiltonian that realizes this. Now, in order to use this to create a subsystem SPT, what you do is you transform it to a state on a bilayer using the same function f, but now instead of depending on z, it depends on z on the first layer multiplied by z on the second layer. And once you do this, now you can stack this, you can write down some Hamiltonian that realizes this state, and you can stack it on top of your trivial paramagnetic phase. And okay, so why do we have to do this? This is so that now you can look at the state. All the orthogonal symmetries act trivially on this state. So now this is guaranteed to be symmetric under orthogonal symmetries, and it's also symmetric under in-plane symmetries just by the fact that this original state was symmetric. And if the original state was non-trivial, this is now also non-trivial. So we've constructed some non-trivial state, but it only looks non-trivial within a 2D plane. It's sort of trivially non-trivial because it's sort of non-trivial in a 2D way. And so I'm going to define any phase realizable by this operation or repeated such operations as weak. On the Fracton side, there's also a way to interpret this stacking procedure. So you start off with a normal X-cube model. You take some plane of torque code or double semyon. Let's just say it's double semyon where E is a boson, but now M and EM are semyons. You can go through some condensation transition where you condense E along with a fracton dipole on this plane. And what this does is it ends up confining this linon. It confines this M particle. But what remains deconfined is this bound state of L and M. So initially the Lineon you could think of as just some boson. Now you sort of attach a semyon to it. So now this model has Lineons that behave as like semyons. And so there's a family of phases constructible by this construction. You can sort of generalize from a single layer to like multiple layers of like quantum doubles, and you can always do this. And this is the same set of phases that's constructible by this other more well-known method of p-string condensation. Right. So in the model that I just constructed, what you find is that if you look at this braiding procedure, you have two Lineons here. You move this one here, you move that one there, move that one back, you move that one back. And they're both on some plane Z. You can divide it by sort of the procedure where you just move them without braiding. And this gives you some statistical phase. And now in our model, if you look at this phase, this function of C, it's trivial everywhere except for the plane where we stacked this double semyon. So, right, and so it's definitely non-trivial, but in principle, we can choose to do this procedure on sort of any selection of planes we want, right? We can choose to stack, to give them semyon statistics on any selection of plane, and each would represent a completely valid, distinct phase of matter. You can't, by arbitrary local perturbations, you can't change any of these statistical phases. And what immediately comes out of this is that, well, how many phases do you have? Well, if you go to L equals infinity, you really have uncountably infinite phases, right? You can choose this phase to be -1 on any arbitrary selection of planes. So there's at least as many phases as infinite binary strings, which is an uncountably infinite set. And when you have having a classification that has uncountably infinity phases, it's not very useful. It's like classifying phases by the real numbers, right? It's not very useful. So what I'm going to propose is, okay, let's define an equivalence relation. Let me define a strong equivalence class, classes which are basically all SSPT phases, but you mod out by all these weak ones. So any two phases you can get to by sort of stacking lower dimensional phases sort of belong to the same equivalence class. And what you do when you do this is, what you find when you do this is that, well, sort of all previously constructed phases that people studied in the literature, X cube is sort of trivially weak, but also people have constructed semiotic X cube, which is really this model, but where you do this on every plane, that also turns out to be weak. People have made all sorts of various twisted X cube models. Those also turn out to be weak. So then the natural question is, well, do any strong phases exist? And what would they look like? And that's the question we're going to ask. We're going to ask now. And the answer is yes. So how do we view this 3 plus 1D SSPT? Well, you can always compactify Z direction and view it as sort of a quasi two-dimensional system, but now there's a sub-extensively there's a symmetry group that goes as Z2 to the L. So it's a 2D system, but with a huge, giant symmetry group. And now we can look at the classification of this 2D SPT in terms of as a 2D SPT. So this is given by the group cohomology H3 of Z to the L. And furthermore, we focus only on phases with abelian gauge duals. And then when you gauge it, you end up with some topological order that's described by a sort of 2L by 2L K matrix that's of this form, where on the diagonals you have two identities, but then on the off diagonals, on the diagonal you have an L by L matrix that's an integer matrix that is symmetric and with even diagonals, and it's only well-defined sort of mod 2 for the off-diagonal elements. And you can sort of think of the off-diagonal elements as they arise from these type 2 cocycles, and they really control the mutual statistics of your gauge fluxes. And the diagonal elements sort of control your self-statistics of gauge fluxes. So, okay, so this is sort of if you just had an arbitrary 2D SPT with symmetry group C to the L, but because our system came from a subsystem SPT, it must have been symmetric under these orthogonal symmetries. And it turns out that that means that you have, actually not all M matrices are realizable. You have some subset of these M matrices that are realizable. And and you can show that there's basically two constraints that it has to satisfy, which is if you sort of sum over all j, it has to be 0 mod 2 for any I. But also the sum of all the elements I have has to be 0 mod 2. And you can roughly think of this as arising from the fact that sort of the stack of all gauge fluxes fuses to vacuum, roughly. And the pictorial way to view this is, let's say we just view M as an adjacency matrix that describes a graph with L vertices, where the off-diagonal elements are these edges that connect two different points, and the diagonal elements, MII, are sort of self-loops. Then these two constraints have a simple interpretation, which is the constraint one is that each vertex needs to have an even number of edges connecting to it, and the total number of edges has to be even. And there's also additional physical constraint, which is that Mij has to be local, so you can't connect two of them that are arbitrarily far away because that would require some non-local term in your Hamiltonian. Okay. So then now what does the stacking look like? Let's say we start off with some existing SSPT that maybe is defined by some graph that looks like this. Now we stack on a 2D SPT that's maybe, this is a bilayer, so it has two vertices. It's described by some graph on it, let's just say it's this. When you stack them, you just add the graphs together, and the edges are defined mod 2. So you can think of stacking as sort of arbitrary constraint-obeying local rewirings of this graph. And from simply this, you see that there's a single strong invariant. That is, if you make a cut across your system, and you count the parity of lines that cut it, this is an invariant of your. This is an invariant. You can basically think of the constraint as being some divergence-free constraint. So if you look at each side there has to be an even amount of lines going out. So there's some Z2 divergence-free constraint. And then you're allowed to add or remove closed loops. And you can see that this can't really change the total amount of lines crossing this cut unless you do some global change, which is not a stack of 2D systems. So there's a single invariant. And what you can prove is that actually here I sort of compactify the z direction, but if you compactify x or y, this invariant has to be the same on every direction. So from this you can see that strong phases form the Z2 class, assuming that this picture is complete. And okay, so what does this strong phase look like? Well, in a weak phase, I told you before, you can have this grading phase. It can be -1 to some p, where p is 0 or 1, and you can choose this arbitrarily on whatever plane, on whatever reflection you want. So this is a weak phase, but in a strong phase, what you find is that the result of this grading procedure gives you an I times -1 to whatever selection of choices you can make. And this I, you actually, if it exists somewhere on one plane, it actually has to be the same for every plane, every direction. So it's some global invariant of your whole system. And okay, and so every model constructed thus far has sort of looked like this. I've told you that if this could be realized, it would be strong, but I haven't shown you that it's realizable. And the way I can prove that it's realizable is by making an example that does have it. So there's really, so with all these other twisted fracton models, there's sort of a construction for them. You can construct them out of lower dimensional SPT, lower dimensional topological orders or something. There's this coupled layer construction, but these can all only make weak phases. To make strong phases, there's really no such construction like that, and you really have to sort of just be creative and come up with a model. And so that's what I managed to do. You have this complicated looking term in your Hamiltonian. There's a b, which is a product of x's, z's, s's, which is the square root of z, and control z's, as well as the usual z terms from your x cube. And so if you take a product of all of these in a huge cube, you end up with some wireframe operator that you can think of as makes your line-ons. And you can easily check from this that lines in this model have an I braiding statistic. Okay, so this was all for Z2 with 3 folded cases, but you can also do this a similar analysis for other cases. So this is what we just went through. So for 3 folded, there's really only one strong phase in a Z2 classification for any G that's Z2n. So as long as there's an even, it's a cyclic group of even order, this is the Z2 classification for 3 folded cases. But if you go down to 2 folded cases, there's, again, you have this type 1 strong phase, that's Z2 classification, but then you also have this more complicated type 2 strong phases, which can only exist if sort of G is Zn cross Zn group, and then a Zn classification. And for 1 folded cases, all phases are weak. Right, and this
Is it only the number of variation that's important?
The number of
they are not perpendicular or something?
it's only the number. And right, and my conjecture is that if you go to 4 or 5, they all look like 3 foliations. And it only depends on the on-site symmetry group. It doesn't depend on like, the space. It doesn't depend on anything else, just the on-site.
But it does depend on the type of places cube.
It depends on whether it's 2 or 3 foliations.
So for all lattices, for all 16 Grabé lattices,
If you can define it with like two players, sets of planar symmetries that are non-parallel, then yeah.
So it doesn't depend on dimensionality either? Or like does a middle column apply for 2D SSPTs?
No, 3D.
Oh, okay.
3D with 2 foliation symmetries. Okay, so I told you about type 1, but type 2, there's also a picture for it in terms of braiding phases. So in this case, we want to consider a fracton model where the fractons have braiding statistics. And suppose you have 2 flavors of fractons, you can define a braiding procedure as follows. So you have fracton dipole here where this one's on plane Z, this one's on plane plus infinity, this one's also on plane Z, this one's on plane minus infinity. And you can again define a braiding procedure where you sort of move it like that. And this gives you some phase that depends on their flavors. And in a weak phase, the way that you make a non-trivial model like this is you basically attach 2D anions to these fractons such that when you braid them, you inherit this braiding phase from the 2D anions that are attached to them. But what you find is that in that construction, you always end up with the braiding phase for A and B being the same as the braiding phase for B and A, simply because for 2D anions, the braiding is symmetric. But if you're in a strong phase, this phase is actually not the same. And the way you can see that is that this process isn't actually symmetric about interchanging A and B, because the first argument here has its partner at plus infinity, but the second argument has its partner at minus infinity. So if you're in a strong phase, somehow your fractons that you're braiding have to be aware whether their partners are at plus infinity or minus infinity, and that makes a difference in their braiding phase. And this is what I call type 2 strong phase.
Can you do the same thing on the torus,
Um,
which doesn't have plus or minus infinity?
yeah, you just have to make it far enough so that you just need to make sure this has no statistical phases with any of these other guys. It just has to be far enough for it. Okay. So let me just quickly summarize. I'm out of time. So I've just approached this problem of classifying fracton phases just by looking at a subset of fracton phases that happen to be more tractable than the whole class of fracton phases. And this is done by looking at their ungauged SSPTs. And so I've identified what are signatures of strong phases and constructed explicit examples. I also have an example that does this, but it's more complicated. And what you find is that in these strong phases, these quasiparticle excitations have some truly 3D statistical phase. And what I mean by that is, very heuristically, there's 2 types of strong phases. Type 1 is where your braiding phase of some quasiparticle in itself, you can think of as not being equal to the square of an exchange phase. The type 2 is sort of the failure of braiding to be symmetric. And Right, and this happens if you try to think of like a single fracton or a single Lineon as being some deconfined particle. You find that it has these strange properties that you aren't really possible from two-dimensional anyons. Yeah. Okay. Future direction, non-abelian fractons. Can we do a full classification of these fractons beyond just strong Clevitz classes? It's also the question of their foliation or entanglement structure. Fractal symmetry is obviously a big one. It's David, other collaborators, Faji, E.G. is here. Lona, Dominic, Wilbur, Juven. Thanks.
Questions?
Yeah.
So is the expectation that the classification of the SSPT phase matches the classification after gauging?
So each distinct SSPT corresponds to a distinct fracton phase, but it's not complete.
But can two different SSPTs gauge to the same fracton phase?
No, no.
Why not?
If
For ordinary symmetries, we know that can happen.
Means relabeling the.
Oh, related.
Related.
Yeah. You can all up to automorphisms like that. Yeah. Then multiple of them can match the same phase.
So you can take that into account.
Yeah, but now you can't really permute sort of like fractons and Lineons are actually distinct, so
Sure.
you can't permute them, but you can permute Lineons within themselves
with
and also
other
fractons within themselves, and you're allowed to do that. Yeah.
Yeah, you construct this model. Do you think there's any hope of having a simpler
Which
model?
one?
I mean, it looked a bit scary, right? The one
Oh.
with the,
This one.
I don't even know how to describe it.
I really don't know if you can make it any simpler. You can write down what I did is I wrote down a computer program that just like manipulates the symbols. And it's like, okay, if I move an X class past like a control Z, it like leaves a Z or something. And then I generated these using the computer and solved it while it cleans everything works out. But yeah, I spent like days drawing and trying to figure this one out. But, I just kept forgetting factors of I or -1 or something. It was painful.
Okay, sense.